right, we're on part 3. Yay! So part 3 reviews the dependent or paired or related t-test. Again, all of those names refer to the same thing. So again, T for 2. Again, I have 2 cups of tea, but now the 2 cups are just for me. Or you get the 2 cups of tea. The idea being it's the same sample of individuals and I am testing them twice. Again, T can only happen with 2 time points or 2 groups. And so we're working with time points. With the paired, related, or dependent t-test, again, I still am going to want a normal distribution. I am still going to want data or continuous data as my outcome variable. And now my time points are going to be, now the most common way of looking at it is looking at time points, looking at pre and post, right? So what was my stress level before we had online class, our classes went online? What is my stress level after our classes went online? What is my stress level before I started work? What is my stress level after I started work? Or what is my stress level when I was working? What is my stress level now that I've lost my job? So again, it's looking at pre, post, or before and after, or baseline. What was my stress level when I had no kids? What is my stress level with kids? Looking at, again, there's a lot of different comparisons you can make with this. And again, the key is it's a dependent or it's paired for your t-test. When we look at our t-test, this is our formula for t-test. Our t-test is still conceptually mean differences over estimated standard error. When we look at our formulas for our dependent or paired or related samples t-test, that Emma D refers to a difference score. So your difference score, all you're doing is taking my stress level before going online and my stress level after going online and getting a different score for each one. So each individual would have this new score, which we could call a difference score. And then the denominator is looking at our estimated standard error. So our estimated standard error, again, looks very, very similar to our z-test, where we had to take variance or standard deviation as well as sample size into account. And so to do that, I would have gotten a standard deviation score or a variance score. Remember, S is standard deviation, S squared is variance, and so if it was standard deviation, I take it over the square root of n. If it's variance, I take variance over n and take the square root. Again, we hadn't, oh, and I forgot the sigma on the slide. So it is sum of squares over n minus 1 is your formula for standard deviation as well as your formula for variance. And so again, I'm not going to have you go through and calculate those things, and but that's what's used to get to our estimated standard error. Once we've calculated our t, again, we would still go through those same steps. We would still go through degrees of freedom. Degrees of freedom, since we have one sample, is just n minus 1. The number of people, again, your people need both the pre and the post. And once you have a complete set, 2 data points for each person, you would go through and do the n minus 1. So if I had 20 people in my sample asking them about stress, my degrees of freedom would be 19. 20 minus 1. And so with our t, we get our t, then we make our decision. Again, the decisions are going to be the same. Fail to reject the null or reject the null for our decision. Then we bring it back to our context. Once we've done that, we still are doing Cohens D, but Cohens D would be calculated a little bit differently. It would be still the top of your t, your mean difference score, divided by standard deviation. So you would have taken the standard deviation you would have used in calculating estimated standard error and divided it by that, and that would have been your Cohens D. Your Cohens D is still the same distribution as what I had talked about in part 1 for your independent t-test. Again, if a D is less than 0.2, there's no effect. Again, if a D is less than 0.2, there's no effect. Once it's at 0.2, it's small. Once it's at 0.5, it's medium. Once it's at 0.8, It's large. When we think about D, also don't worry about negatives. If you had a negative for the top of your t-test with your mean difference score, you would just ignore the negative. So I'm going to go back to this idea of Facebook, and I'm going to say, well, I'm interested in seeing, do I see differences in number of mutual friends pre-COVID-19 and post-COVID-19. So maybe I'm trying to spend more time on Facebook online connecting to my people now that there's more social distancing. And maybe through making those connections, more people are finding mutual friends. So let's look at that. So in this case, it is made up data, loosely based on some data we had from our independent research design on Facebook. And so I'm pulling out, again, here's kind of how the data set is set up. It's set up a little bit differently than an independent t-test, but I'm not going to go into that with you guys. But just know we set files up differently depending on our design. And so again, that degrees of freedom is 29, because now with our dependent t-test, it's just n-1. This is the t-value that it was calculated with. So again, that t-value I got from here with my output, my p-value. Again, this is the exact p-value for this t-value. So again, I don't need to go and find critical values in the real world. So I can see p is 0.003. Oh my gosh, is that significant? Yes, it is. It is less than 0.05. And then I can also see it does calculate, my image kind of covers this up, but it does calculate Cohens D, and Cohens D here is 0.596. So 0.596, if I were to go back and look, is part of that medium. It's a medium effect. So again, the other output that's nice that gives you in a pair t-test is it gives you the top of your t, and it gives you the bottom of the t. So the top of my t, my mean differences, looking at, again, I would have created a difference score between all of these. So I had 4 more friends for subject 1, no more extra friends for subject 2. I had 2 more friends for subject 3, again, getting that difference score. And then I get a mean difference score. That mean difference score is 0.733 friends. I've added an average of 0.733 friends after COVID. And then I divide that by my standard error, my mean difference, which is that bottom of t, and that's how we get that t of 0.327. Again, when you have output, you can also see the mean. So my average friends pre was around 22. My average friends after was around 30 something. And again, my standard deviations for this made up data is around 7. With the average variance for number of friends across pre-COVID and post-COVID. Again, kind of fake data there. So again, paired t-test, related t-test, dependent t-test, all the same thing. It's the same individuals being tested twice. This is part of what's called that within subjects design, or that repeated measures design. Again, the same people are being repeated. I'm getting that outcome again at time 1 or time 2 or pre or post or baseline or after my drug or intervention or experiment. When we use a dependent T, that typically gives us more power. And the reason it does is because you have the same individuals. You're able to see individual difference with that change in time. And so that's giving us more power. And again, you would learn more about that in research methods class, but just an interesting thing to note. When we think about it again, we can think about some ideas. What could we get from Facebook if we are able to time capture for pre, post, before, after measures, or time 1, time 2 measures, or again, control experiment? So I encourage you, what kinds of questions would you have that you would use a dependent, paired, or related t-test? And again, I will tell you, there's questions we can ask that you could use either an independent, and I could take 2 different groups. I could also use it as a dependent and take the same people measured over time. There's caveats to both, pros and cons, and you will learn more about that in research methods. So some key points, again, it's part of that repeated measures or within subjects design. I still need a normal distribution. I am testing the same individuals twice, so because of that, I don't have to worry about that equality of variance that we worried about with the independent t-test. I still want to have a t that's pretty big outside that 0 range. A t of 0 means there's no differences going on there. When I looked at the mean differences, it would have been 0. And so a t of 0 is not what I want. A t of 0 says there's no differences. Again, I want a larger number. How big is that number? Well, that's going to be dependent on my sample size and connected to that idea of critical values. If it's large and I get a p less than 0.05, again, that alpha of 0.05 being my marker, then I can say I can reject the null. When I reject the null, I'm saying there's significant differences. And then if I don't get a p less than 0.05, then I'm part of that failed to reject the null range, which means I don't have significance. Regardless if I have significance or not, if I fail to reject the null or I've rejected the null, I want to do effect size tests. Again, effect size test is Cohens D. I could also have used the R squared. R squared is the percentage of variance explained from your outcome by your groupings or your independent variable. And I had showed you the example, the formula for that in the independent t, but I didn't talk about it too much because I was running close to that 15-minute marker. But it really is, it's t squared over t squared plus the degrees of freedom that you used in calculating your degrees of freedom. And so again, I focused more in our example with our output. We had Cohens D, and Cohens D has those ranges. Power is connected to sample size. Oftentimes, if I want, if I'm concerned about the ability to find significance, I could run some power analyses. And then speaking of power, when I have a dependent t, I typically have more power because I have the same individuals across both groups. That's going to give me less variance because it's the same people being tested 2 times. And again, the way you would write up and see a t for dependent means or paired or related t-test is going to be the same. Right up with the t in parentheses, degrees of freedom, then you give your t-value, comma, p less than 0.05 if you add significance. And then you could share d. So some wrap up, we learned about T for 2. It's all about those 2 groups of 2, compares 2 things. Again, I need a normal distribution, I need data. We talked about the 3 different types of t-tests, and again, that's going to be based on your design and what you're doing. Are you working with samples or one sample with the population? Do you have an independent or paired or dependent? Again, it's going to be going back to that design. And then think about some of those differences between our t's when we're comparing the independent t and the related measures or the paired or the dependent t. Think about differences between those 2. So homework, you are going to have a reading quiz. The reading quiz, I call it a reading quiz, but it's really based from lecture material, based on this video lecture, based on, also you can look up these concepts I've talked about in your book as well. And then you've got part 1 this week, which is Mythbusters. And again, you don't have to do that one first. You could do the Facebook one first. The Facebook one is that part 2. So you have 2 parts to your homework to make up the 20 points this week. And then there's going to be an optional discussion board. What questions do you have still related to T? I hope you have a great week, and I hope that you're adjusting well to our online learning. And please reach out to me and contact me if you're struggling with anything or if you're needing additional resources. I am here for you. Thank you.